Okay, I will start slowly so people can catch up. Okay, so I mean, maybe yesterday for the first lecture, maybe a bit too much material I found. You know, it's always the same problems trying to tune for new lectures, I mean, on fly. So here I'll try to give as many example as possible and go slow. We have still a few lectures after that. And okay, so I added the, I don't know which version you have, but I mean, I added a couple of slides just to remind for people who were in the first lecture that in fact what we did simply yesterday for the first lecture is to build a couple of detector in E plus C minus a collider running at epsilon 4s resonance. And now the whole sentence should be more or less clear for all of you. And when we did that, I mean, we tried to design our detector such a way that we maximize the advantage of a clean environment. And now that you see those event display, you should be able by eye almost to do your analysis. And you know, if you are brave enough, you do that over million of events, event display, and then you collect those with some of the final state to mention here, listed here, and to reconstruct some real B candidates. And you see slowly building up some peak and identify as basically your B signal. So just to remind you that actually what we were looking for here are actually dominant standard model BDKs. In fact, the BDKs has so many decays, and even the dominant one is in order of 10 to the minus 2, or very often 10 to the minus 3 already. So just as an example, B plus to D0 pi plus that we study among the mode here are basically 0.5% branching ratio. So, you know, not even for a B factory, then you need to accumulate a lot of those events actually to study rare BDKs. So again, I'll try to go step by step because I have maybe to explain a bit more what I mean by rare BDKs. Especially those days, rare is not necessarily as rare as it used to be. And the rare is a bit used at, you know, in contrast of the dominant decay I just mentioned, the B to C transition, okay, which is the most favored. So of course, the dominant decays are not rare. The phase-space suppressed decays actually are not considered as rare. Even the Cabibbo suppressed decays, I mean, some call already them rare, but in our today talk, so the B to U transition typically compared to the B to C transition is of course suppressed and but not called rare in this lecture. B to charmless mode, we say very often, are in the category of rare, but what we call today in terms of new physics search will not be those rare BDKs. I put also other, and probably I will use some of those jargon. For example, the Cabibbo suppressed decays here, I just mentioned, are typically already suppressed compared to the favored decays by 1 or 2 order of magnitudes. So there is a color suppress also, very similarly, but this time instead of external diagram, Feynman diagram, you will see an internal one. And again, not really rare, even if the branching ratio start to drop, we already in the world of 10 minus 3, 10 minus 4. Now we start to come in the rare decay categories, if you want. And I will here mentioned the category of hadronic flavor changing neutral current. Basically, the B to 5K short. I might mention this kind. I put the diagram here, B to C, with a gluon which pop up here SS bar pair, and which allow you to have as final state this 5K short, which is CP state. But that will not be the purpose of the lecture. There is some interest, a bit similarly to the rare decays we will study, and I might mention in the last lecture. So what I will call rare decays are basically the electroic penguins rare decays. We talk about mostly two kind of decays. The B2S transition, in fact, so very suppressed in the same flavor, B2S, B2S gamma, or B2S LL, L plus, L minus, a pair of leptons, and related to that. So the B2S gamma is one of the rare BDKs, which was studied the most, especially from the Cleo time. And as I will show, we have a specific advantage in the B factory because the whole final state can be almost as easily reconstructed despite of having a neutral, so photon in the final state, than efficiency is very similar to the dominant mode efficiency. And let's say the B to SLL, which is even more suppressed, and by the diversity of the diagram involved, actually is even more an open window to the new physics. So those are the standard model respective Feynman diagram. And as you know, probably the motivation of new physics is to get through those rare decays and verify the agreement or not with the standard model, hoping to open this window to new physics. Here I put some summary, a contrast between direct and indirect search. So in the left part here, top left, I just mentioned the complementarity with LHC, looking for those direct search, so direct signature of new physics, but without, until now at least, much success. And hopefully with higher energy, higher luminosity, something will finally appear. But for now, this search is, let's say, not successful for the new physics. Well, successful because it brings very tighter and tighter constraint. However, not yet some observation. So that's what I was calling yesterday the energy frontier, which is always limited by beam energy, and people already think about what higher energy could be reachable with a collider. Whereas we are working, as we discussed yesterday, on the intensity frontier. So this time we will study those rare decays with, branching ratio very suppressed. And actually, I borrow this summary from Endosan at KK, a colleague of KK, who, classify, if you want, the search for new physics in kind of three categories. The first one concern, in fact, those, and I will show a few, typically what we call RD star, which is the decay B to D star tau nu or D tau nu. So where it's a standard model actually decays, so a B to C, and this time a tau nu, so W decaying tau nu, where the new physics can compete. But here, one of the issue is that actually you have to be extremely precise because the standard model is very dominant. So this is a measure which is not trivial because you have to compete with a standard model, which is very dominant. Your new physics will be, if you want, a modest effect compared to a large effect from the standard model. In the second category, we are in the loop. We are talking about the B2S gamma transition, where the standard model and new physics could be at the same level. So you have an interference here. So you will look for, of course, an effect on the branching ratio, but also effect on the CP, for example, direct CP or CP violation, a time-dependent CP violation, where you expect that this contribution, this interference with a different phase, for example, can appear in these CP parameters. And the last category is where the standard model is doesn't allow this decay. Typically, this lepton flavor violation decays, where you expect no signal, or you have a very strange, unexpected signature. And if you see this decay, and then, well, it's perfect. Because, I mean, as it's forbidden in standard model, you have a clear signature of new physics. Toward the end of the third lectures, I will talk about this lepton flavor violation in B decays and later in tau decays. So we are in the second category where we expect here I mentioned with the parameter I mentioned the branching ratio, of course. So to see if this decay rate is enhanced or suppressed, or again introducing those new source of CP violation. And here, sorry, and here we are talking about for example, charge asymmetry, and I will show few examples of this. There is also a very, especially when it's possible, not in B2S gamma, but in B2SLL, most certainly Guy in his lecture on LHCb will show much more details of angular analysis, where in the B2SLL, we also study possible departure from the standard model. So yeah, in summary, in one side for this part, what is the very interesting part of this rare decays is that you expect some, you know, the place where you want to be. It means the effect is sufficiently large compared to your precision in terms of experimental precision and your control of the systematic uncertainty. If it's a tiny effect, here I talk about 1% or less, then you will compete in the systematic. So we go back to the let's say naive conclusion we had with the Rutherford experiment of controlling your environment with the higher accuracy. And the other part I didn't mention, and probably I will illustrate with the few cases, for example, Bisabas to mu mu, where we should insist that also not only the experimental side should be clean or should be under control, but also those observables, we have to make sure that, I mean, you will get, I mean, you have a theoretical control, if you want, of your observable, at least at the order of the experimental sensitivity. So for the indirect search, I wanted to give a classic example. So because I just say that, you know, new physics, if you want, can enhance or suppress those decay rates of rare decays. And well, in the few examples I could listed from indirect search, I pick up a classic one of the decay. So, I mean, in the context here of the kaon physics, but you could imagine, you know, replacing the k long by a Bisabas or B0. So anyway, so in this classic example, you search for K-long to 2 muons. So you see a signature which now become very usual. I mean, it was the case for the epsilon. It would be the case for, of course, it was also the case for gypsy, for Bissebes. The 2 muons are, especially in more difficult environment, are really kind of experimental golden mode because of its robustness to detection for compared to the background. So you look for K-long mu mu, and at that time you can, with a standard model of that time with a 3 quark, you can calculate the branching ratio that you expect, and you find something in order of 10 to the minus 4, and you do the measurement and you don't find anything, or you find something much a limit, in fact, much lower than 10 to the minus 4. And actually, I took something a bit more recent. I mean, the real measurement after being observed was is 10 to the minus 9. So you see a huge difference between your standard model and your measurement. So this is almost, I mean, this is a classic case of successful indirect search. And then as you all know, the fourth quark come at the, in fact, new physics of that time, if you want, an extension of the standard model at least, and which explain this cancellation between these two contributions. Then you can even, in fact, because if it's perfect cancellation, if C has the same mass than the up quark, then you will have perfect cancellation. It means basically you will never observe K-long to mu. And here you can observe something at 10 to the minus 9. So you have a constraint, an idea. So the indirect search actually allow you to conclude that you should look so indirectly you have this information, then you should your conclusion that you should look for sham quark mass around 1.3 GeV, and to get the predicted rate this time using this contribution at the order of an observation at 10 to the minus 9. Okay, so however, so now the second advantage is that I mean, yeah, the main, I mean, of course, it's already, you have a good, not a direct observation, but a good indication of where to look. So it becomes, the key point, if you want, to design the next generation of detector. And you find again this kind of synergy, or this kind of double quest for a new physics, where you have two kind of way, or two tools, or two kind of tools to aim for this new physics. Now that in fact, what energy, or what, I mean, what in this case, what is the mass of the particle you are looking for. So if you have a C quark at 1.3 GeV, you must have CC bar state around 3 GeV. And for that, you have two possible directions, as you know, but now illustrated in our context of a fixed target experiment where you shoot proton beam. But here you have to get a much larger energy to obtain this, or to produce, sorry, this CC bar state. Or you have, let's say, kind of a scan-like experiment, where this time you have here two electron-positron of about same energy in these cases, and you scan, you increase the energy starting let's say at 2 GeV, and going step by step at higher energy until you meet the energy corresponding to the mass of your CC bar state, and you will see this resonance. And you go beyond and you see the whole resonances. And as we discuss later, and this was why we were talking about the dimuons being important. And we have seen also for the reconstruction of the B decays that random combination of other particle give you the background which is under your peak. And this is an illustration here of what we would expect after reconstructing the invariant mass of all the two body combination, where after selecting, of course, your muon to suppress this background. So this is exactly the way it has been done. And the two paths, if you want, of course, fixed target experiment in one side, and you know, typically here this time instead of, I was talking about 2 muons, we'll see later, but in 2 other lepton, 2 electron, and this is very interesting because you will see also electron versus muon later, and yeah, you got the result of team group versus the search on E plus E minus collider, where they start from 2.4 GeV, but by 0.2 GeV step at slack in this Mach 1 detector, and then increase until they observe this bump. I mean, a bit more than a bump in at 3 GeV, confirming. I mean, or confirming, observing this jet psi particle, which is a CC bar mesons, and so a direct discovery of the force quark. So this is, yeah, it's just what we would like to have, or we expect to have when you follow the indirect search path. It means so in our context, Belle II in plus E minus, LHC B in proton-proton. I mean, would find a sign of new physics in their rare B search, and indicate or favored some of the model which are being discussed in the other lectures. Okay, so just in summary, just very quickly, I also try to illustrate another of these indirect or search which came before the direct search and kind of enhance or trust or beliefs that we are on the right path. And so this is also another example where here you have a neutrino beam in this Gagan bubble chamber, and you see in fact a very clear signal of the appearance of electron, if you want, which would indirectly show that you have seen what you expect to be a Z0 boson. And of course, a more dedicated experiments are put in place and designed very much like what we have today, almost setting the set of all those next experiment, which exactly, so this is why I put this lecture as this figure, sorry, because it's illustrated exactly, perfectly what we have discussed about the layout of a detector and, the logic of its subcomponents for a target, which was the observation, and then again on some old event display, where for the zero is quite striking, the analogy that we have with what I show for J-psi and epsilon, and what we will talk about for B2 SLL. And of course, the invariant mass here of the 2 leptons, and something a bit similar, but I will not go in detail for this time, the W. So let me, in the rest of this lecture, go through this time the radiative B decays. So I go back to this rare mode we were talking about, B2S gamma. And actually, I will take two sides of this observation of these decays, how we can study it. I will talk about exclusive and I will talk about inclusive. But those are the famous penguin, and you have all these stories around the penguin. I will find how to say, impressive the effort of people to make the diagram as close as possible as looking as a penguin, and I put here very nice artist view of the famous penguin. And this decay has been observed for the first time in the 90s by the Cleo experiment. So you remember the kind of ancestor of the B factory with a symmetric collider E plus E minus with a symmetric collider. So it's, again, very similar to what I have shown for this dominant decay, where with the first Belle II data, we were reconstructing the same decay, B to D pi, with a different D final state, D decays, and some with K pi, some with pi 0 in the final state, some with K short. And so for the first observation of B to S gamma in exclusive mode, so the exclusive mode is B to K star gamma, and K star can decay in in different final state, K star 0 to K minus pi plus, K star plus to K minus pi 0, or K short pi minus. Sorry, I mean, you might not see the white component, which is these few entries. And very similarly, but with different color code, you see a building on this MBC variable, a sign of your signal. So you need here the whole statistic to obtain this small observation. So you give already a first branching ratio with a modest precision. Of course, today with the Bell statistics, and tomorrow, I mean, today already in Belle II with an equivalent statistics, but tomorrow with even much more statistics, then you can see this, many decay mode with a much larger yield. And here you can see that, your few events you have today correspond to several thousand events. And this time you can, so here you see, okay, so you see the different final state I have been mentioned. So the K minus pi plus, the K minus pi 0, and the K short pi plus, with a ton more of statistics, and also other final state like K short pi 0, which will be particularly interesting to study a CP violation. You have a K short pi 0 gamma in the final state. And then with the statistic, as I said, I mean, you obtain a very precise, we were talking about, basically 20% precision for the branching ratio for the Cleo measurement. And then you reach, at the order of a couple percent. So you really ping as much as possible at the level of the systematic uncertainty, your branching ratio measurement for neutral B decays and charged B decays in those penguins. So you really change regime, if you want, from the first observation to something very precise that you can compare to the theory. As I mentioned earlier, this is the ultimate case, and now we will talk about how clean is the theory and should be the experimental measurements. So why we separated? So we separated this K minus pi plus in two categories. In fact, the B plus and the B minus can be reconstructed separately to measure, in fact, the charge asymmetry and to see if there is a sign of departure from zero. The standard model predict for the standard model, we have a prediction of no asymmetry, and for some model of new physics, you would expect 10 to 20%, at least before you measure it. And here you can see that with these statistics, first I show the branching, a compilation, if you want, of the branching ratio first, and I will show next the asymmetry. So for those branching ratio, you compare to here the theory, which is the large band you have here, compared to actually compared to the experiment. And you see that actually the uncertainty in terms of theoretical branching ratio is very, was quite sufficient until you reach this precision. And here the hadronization process, in fact, limits the ability to predict more precisely than this. And the experiment here, the 2B factories keep updating, and Belle II will do even more precise measurement. But in this observable, you start to see the limitation of the measurements, where the systematic is become larger than your precision. So we just mentioned earlier than the statistical uncertainty is typically of 1–2% here, 2%, while you need to improve much more your detector, or the control much more your detector, if you want to be more precise in those branching ratio measurement. But again, you don't see departure is completely consistent with the standard model, which only allow you to constrain the model which predicted large enhancement. And for the asymmetry, that's what. So now you have to look for other observables, and the asymmetry is one of the very nice experimental observables, in the sense of it's canceling also some of the systematic. As you're measuring B minus and B plus, for example, in this asymmetry, some large, let's say, some large systematic uncertainty coming from the gamma in the final state will be common to these two contribution to the asymmetry, and then will cancel out. You see the same effect. So it allows you to have some systematic, which are this time with the same data sample, which are this time smaller than the statistical uncertainty, so which means that you have more room and you need to do more precise measurement to see if you have some departure. So here you see again the theory also trying, keep improving with those prediction. And maybe this is illustrated with this very small uncertainty for the theory expectation of the standard model for this CP asymmetry, while you are still, you are quite precise at a couple of percent we mentioned earlier, but this time you are not systematic anymore, limited. And you see, by the way, so LHC B for some of the final state where you have especially a single gamma or a single pi zero in the final state entering in the game with a precision which is actually already very interesting and competitive. And those measurements, here the latest from Belle, allow you to test the standard model even more precisely. But again, the room remain to improve at Belle II those measurements, and by the time the Belle II experiment will complete its data set and do analysis on it, you will have an uncertainty smaller than the systematic, and you will be able to measure the asymmetry in the order of 0.5% or less. Yeah.
I'm sorry. In the previous slide, you have mentioned submitted to the PRL. So, is there any update on this measurement for the simultaneous fit of 4 final states?
Yeah. So for those slides, those were the slide I prepared for the latest. So you see here the statistic corresponding. So basically, if you remember in the plot I've shown with the Belle and the Babar statistics, we typically for Belle have at epsilon 4s this sample. So this is the entire sample of Belle. But for Belle II, so this is the final word from Belle. But from Belle II today, we have something getting close to 400 inverse femtobarn. And in few years down the line, you will have a Belle II measurement more precise than this one. Yeah.
So you have, I mean, with the Belle II measurement, there has been a submission to the PRL, and it's going to be published soon. Or is it that statement is from the slides earlier? I mean, in the previous slide you have mentioned.
So yeah. So here this is for the Belle. Yeah. So the first.
Okay. So and it's already there in this table. Okay.
Yeah, exactly. And then yeah, exactly. That exactly is this measurement, 2017. Okay. And so Belle II will come in the future. I will let Sorab make the promise to when, but it's under, let's say, people are working on it, yeah, for Belle II.
Thank you.
Yeah. Okay, so now let me finish, in fact, this part with a limitation I have talked about. So the branching ratio, as I said, it can be, so we have seen the B being able, I mean, we are able to reconstruct the B in different final state in the exclusive mode. So we look at K star gamma. We also can do the same game for K pi pi and so on and so on. And so, but as I mentioned, you have seen that actually because of one, the observable at this precision is not as clean, in the sense of the theoretical prediction is not as good as you would like to be. And so you have to look for other observables. We have seen the asymmetry. There is more you can do with the branching ratio. And here you have a, you know, in an inclusive way, if you want, if you take the B to S gamma inclusively, so almost at the quark level, then the prediction coming from theory is more precise. You don't suffer. So what you say is you don't predict all the different decay, but the sum of the decay, if you want. So this is much easier in some sense for a theorist, or at least they get rid of this limiting factor that I was talking about, the hadronization. Whereas for experimentalists, it's a bit more difficult. An inclusive measurement, how can you measure S gamma? So this is a kind of you know, the contrast of most of the case that you know, when it's easy to predict, then it's difficult to measure, and vice versa, or at least in the remaining observables. So, so just one word about the B2S gamma. I insisted on the fact that, so here, there is always ongoing work, always improvement, and this is why it's so important to interact with theorist colleagues to understand and to probe, you know, or to push them or to convince them then we need those prediction for those and this and that observables, but more importantly, I mean, to have, you know, with the time, more and more stable, more and more developed calculation. And the B2S gamma in this sense is a very good example. Over the time, I think Misiak show, I mean, the theorist, one of the theorists here involved in this calculation, I think once present in conferences, the evolution of the prediction, the improvement at the different steps. So, and you see that when the calculations here to the next leading order, sorry, it's quite poor quality, but then become stable and robust prediction compared to the earlier or let's say the lower order calculation. And then when you know, here the branching fraction becoming a stable and reliable and precise measurement prediction, sorry, and then you get a golden observables, and you see that time that, you know, you have something predicted at, let's say, almost a 5% accuracy. That you still have to measure it, and that's a difficulty in this case. How do you estimate the branching ratio of P to S gamma? So there is, I would say, the kind of brute force method, which consists here of saying, okay, as you have seen, we have discussed in length about the K pi final state, K pi gamma. So I can do K plus pi minus, K short pi plus, K plus pi 0, K short pi 0. Fine, so the four mode, but I need much more modes, and I will pile up. I will try to exhaust, in fact. That's what we call semi-inclusive or sum of exclusive, if you want, probably more appropriate. And then you say, okay, let's go. I mean, well, if you have students brave enough around you, postdoc strong enough to handle the, you know, to handle the work, and then you keep going, and a bit like the game we play at the beginning with the dominant mode, then you will just pile up as many final state as you can. And you see here, this is a list, for example, in this Belle measurement in 2014, where actually they had 38 modes and you know, obtain the result. However, I mean, there is many limitation in terms of experimental side. I mean, if the first mode we have seen looks very clean and undeniable signal with very little crossfeed from the other modes, once you arrive with some final state with a couple of pi 0 or, you know, many or too many particles in the final state, you end up with a lot of crossfeed. So it means feeding from the other mode that you have to understand to sum up properly each contribution, and not having double counting and then screwing your result. So very clean in one side, but becoming very, very dirty and very unreliable in the other side. So, I mean, you still provide a branching ratio of the sum, and you have to extrapolate to the mode that you couldn't measure. And then you end up with this more precise. So here you, if you want, you beat the precision needed to, you know, to the comparison to the prediction. However, you end up with this large systematic, which reflect the fact that you have a difficult, hard time to handle this crossfeed, or to understand this crossfeed in your detector, this contribution from other mode feeding in your in different final state. And also you have to extrapolate to, as I said, this branching ratio to the modes you couldn't measure. So you have to make some assumption of, you know, relation between modes to complete, if you want, your branching ratio measurement. And this add up to the systematic. And you see that it's much larger than what you'd like to be. For the case of B2S gamma, so I go directly to the measurements. What we are doing is the following, in fact, is which I found always very smart, is in fact what we will do is just look at a single gamma in the final state. So here there is a nice illustration of your BB bar decays, epsilon decay, where you will look for a single gamma with a high energy. So the B2S gamma is a two-body, and so the gamma here carry a large energy from your almost at rest B. So in average more than 1 GeV, and you see earlier the spectrum. So this is the energy of your gamma in the center of mass. And so you see in green the signal. But of course, if you just select a single gamma, the combinatorial or the source, the other gamma source other than your signal, the background will be much higher. This is a log scale. And you see a large contribution coming from a continuum. And the idea, so this is another illustration of this center of mass energy of the gamma. You have the background that I was talking about, and the large component is coming from the continuum. So what you're going to do to estimate this contribution is in fact using the following trick. I was saying that we are running mostly at epsilon 4s. And on top of the epsilon contribution, you have this E plus E minus 2QQ bar component, which is your background, which is a continuum I'm talking about, which produce some gamma whose spectrum is shown here in red. And what you're going to do is ask the accelerator to lower the beam energy and to run at a lower energy in the center of mass, just below your resonances, where you are sure to not have BB bar contribution, but only in fact a background contribution. And what you do is, a technique that often used, taking a sideband in experiment physics, you go on site and you take data which are not, directly useful for your search. You don't have signal, but you have only background, but you have a sample directly from the data where you measure your background. And this is very valuable in this analysis. You will use what we call an off-resonance data sample to actually describe your background and subtract it from your distribution that you obtain on resonance. So if the subtraction is done properly, you have then a complete cancellation, if you want, of the continuum contribution of the gamma. The remain, after this subtraction, remain only the contribution from BB bar, which are often coming from a BB bar decay, because you don't have gamma directly from the B decay other than your B2S gamma. And this BB bar contribution is often, in fact, those gammas you are selecting are coming from pi0 eta decays. And that for that, you study the pi0 yield in your detector coming from BB bar and subtract also this contribution. You end up with a spectrum, which is this time huge statistics. You remember the few thousand events for each individual decays. Here you have all the B2S gamma contribution, so the gamma coming from all, and you don't need to reconstruct the except S, sorry, so the chaotic part, the S part with all those finer types, as you reconstruct only a single gamma. And you see the spectrum I was talking about after subtraction from this continuum and subtraction from this BB bar component. So you are able, in fact, to see the B2S gamma. center of mass energy spectrum from this gamma. And then the fact that you have a good agreement with, you know, when you go beyond the kinematic limit, a good agreement with 0 show that your background suppression was done properly. You, of course, there is an efficiency dependence, and then you can correct and obtain, in fact, a branching ratio. And you see this time that you have, at least when the energy is sufficiently high, you have improve your theory, I mean, your systematic control. And this time, what is limiting you is the statistics. So with the time and with the more statistic, you have find a handle, a different handle, a different systematic also. So you have almost, for the same observables, different techniques and independent systematics, which allow you to combine those measurements. With the time and with the control of your environment, you improve and lower the cut, the threshold. So the background is getting much, much higher at low energy. And so you get a better control of your systematic with this kind of effort. And this would be a very a nice, when you observables to compare to theory. So this is where, you know, come everything to the end. The effort of theorists I have shown with the precision mentioned here, the best shot of theory compared to the combined measurement of this different approach with let's say, similar now uncertainty. So you have a competitive measurements, which, you know, those comparisons, so the combined experimental measurement with this precision in the order of the theory area I was mentioning, so side by side. So you see a very good agreement, unfortunately, with the standard model, but which allow you, and this is just a single plot for the conclusion, which allow you to constrain strongly. Actually, this is one of the strongest constraint of coming from rare B decays in B factories time, which allow you to constrain some of the model, like, for example, charge Higgs with a certain model, a certain scenario, to some limit that you cannot even reach today with a direct search. And so that show exactly, so if the Higgs, charge Higgs of more than a certain, of less than a certain mass, sorry, would exist, and you would have seen enhancements. And so you get a limit because you don't see a departure from the prediction of the standard model. Okay, that was my last slide, and I will end up with this, you know, B2S gamma example of B factories. And in the next lecture later today, I will mention about leptons in the B decays. Thank you.
Okay. Thanks a lot, Karim. Are there any questions?
Jim, can I ask one? Just curiosity question.
Sure, Namit.
Karim, in the previous slide where you showed the one more, please. Sorry. Yeah. So if you look at E gamma star greater than 1.7 GeV versus 2 GeV, statistics probably is lower for more than 2 GeV. So the statistical error is large. That's what I'm. But the systematic somehow goes down. Is there a way to understand, or I was just curious about this.
You are talking about what is in green versus what is in black?
No, blue versus black.
I'm trying to find what I did here. Yeah, yeah, you're right. Yeah, I wouldn't expect. Yeah, so I think here, yeah, because here's the measurement. Yeah, okay, I got. Sorry. Here, in fact, this difference of systematic, I think, is due to the extrapolation. So you do the measurement until 2 GeV, and here, as you go, I know actually, as you go at lower energy of the gamma, then this reliability, in fact, in the information you have added between 1.7 and 2 GeV is actually increasing your systematic. In fact, it just reflects this difference. This is what I was talking about, is this difference you see. So you gain in statistics, but you lose in systematic. So it means that the data you have added, if you want, suffer from a much larger systematic. So this is exactly the effect I was talking about. So it means that for now, if you want, you have the systematic limitation of your measurement while you want to go. What you want to do experimentally, of course, ideally, the prediction you have shown is valid from the beginning of the spectrum. So you want to go at 1.6 GeV. If you go at 2 GeV, in fact, you have a limitation, and you need to do this extrapolation. So ideally, what you want to do is to measure it as low as possible. But as I said, as you go at lower than 2 GeV, you have and here we see the after subtraction, but you have to see the plot before subtraction. And what you see this is in log scale. So you see that actually less than 2 GeV, you don't have that much signal, but you definitely have much worse background, much larger background. And this subtraction here is in fact affecting your systematic. You lost control, in fact, of your subtraction. This what give your large systematic.
Thanks.
So what we expect is with more statistics, also larger, something I didn't mention, larger also off-resonance data and a better control of this subtraction, then in fact, this is the limitation of the method, that you will be able to do the measurement at 1.6 GeV, but with a much smaller systematic. But I would say that, you know, for now, even if you do that, even if you improve, in fact, the world average by doing a much more precise measurement, then you will still, you know, be limited by the theory right now.
Thanks, Karim.
Okay.
Okay. Any other questions? If not, Karim will be back this afternoon at some point. I'm not entirely sure when. About, I think 5:30 our time, 2 o'clock your time. Yeah. So thanks, Karim.